Chapter 11 was our counting chapter, where we were given a variety of situations and asked to count how many ways could that occur. So how many ways can you create a 3-digit number using the digits? So in these problems, you're restricted. We can only use digits 0, 1, 2, 3, 4, 5. We couldn't use 6 or 8 if repetition is allowed. So the key thing is they've told us how many digits, they've told us what we can use, and repetition is allowed. So for instance, I could have 2, 2, 2. Now within chapter 11, there is a key idea, which was if you can break up a problem into separate steps that aren't related to each other, they don't affect each other, then you could count the number of ways to do each of those separate steps and multiply it together to get the number of ways to do the entire process. And this is an exact right candidate for this. If we're creating a 3-digit number, would we agree that that could be broken down into the step of picking the first digit, picking the second digit, and then picking a third digit? And remember, these lines don't mean anything. They're just something for me to mentally focus on 3 separate occurrences. So there are 0, 1, 2, 3, 4, 5. There are 6 options, right? How many things could go in the first digit? I've got 6 options in all. 5. I see some people saying 5. That's correct. Remember, the first digit could not have all 6. We can't have 0 here. Because if there's a 0 in the first place, then it's technically a 2-digit number, right? It's not fitting the 3-digit number. Now, since we can repeat, for the second digit, is there any restriction on it? No, 0 can come into play, right? And you can have the number that you already chose. So we could have a 6 there. And then there's no restriction on the last one, right? Also a 6, because we can repeat, and multiplying those together, five times 6 times 6, I think we would get 180 as the number of options. Now, how would this problem be changed if they said, same thing, 3-digit number, repetitions allowed, but it needs to be an even number? I'll give everybody a moment to think about that. Everything else is the same, except you have the additional even number restriction. Think about which of the 3-digit locations, the first digit, the second digit, or the third digit, is affected if the number is even. Do we agree that would only be the last digit? Because the last digit tells you if it's even or odd. So the first 2 digits remain unchanged. You could have 5 options there. You could have 6 options here. Remember, these are the number of options, not the digits themselves, right? Because 6 isn't in the group. But what could you have here is you could only have an even number. So 0, it could end with a 0, a 2, or a 4. That would leave us only with 3 options, because I couldn't end with a 1, a 3, or a 5 and be even. So 5 times 6 times 3, I believe that would give us 90, which makes sense, right? If you've got 3-digit numbers where you allow repetition and if all there's 180, doesn't it make sense that half of those are even, half of those are odd, which is why we get 90. Yeah. And we're not going to ask this, but if I said under 200, so everything plus under 200, which location does that affect? First, second, or third digit? If we say under 200. First digit, right? And in the first digit place, you could only use well, you can't use a 0 because it's a first digit. You could use a 1, and you couldn't use a 2, right? Because that's not under. So it would be like 1, 6, 3. If it was an even number under 200, using only these digits and repetitions allowed, which would give us 18. So I remember from this section where the different aspects come from as you're working through this. I think we might have time for one more from this section. And our goal with this week is we're going to try to review as much as we can, but we want our review to be, thorough. And I do want to prioritize the earlier section of material because that's probably what's a little bit more rusty to us. So that's why we covered the beginning of the semester and we're moving our way forward. So if we don't get to chapter 10 and the later parts of chapter 9, that's okay because that's our most recent material. That's more fresh in our mind. Let's think about question 2 briefly before our class ends. Okay, so 4 singers are going to perform. There's a few ways that you could think about this. They're each 4 going to perform, right? And does order matter? Like if singer A performs before singer B, would that be distinguishable than B going first? Yeah, so order matters. And basically we've got 4 locations, the first concert slot, second slot, third slot, and fourth slot. How many people could be chosen to be the first position? 4. Once you've chosen that person, how many remain for the second position? 3, right? Because somebody's already been chosen and it just decreases like that. So I believe that should be, there are 24 different ways to schedule their appearances. So we currently have 7 books on a bookshelf. How many ways could you select 3 of those books if the order selected matter? Now, as I'm reading through this problem, I notice it has the basic structure of, okay, I've got a larger group of things and I'm selecting from that a smaller group. And from that, we'd recognize permutation or combination, right? How do you decide between the two? In permutation, order matters, and in combination, order does not matter. So that's the idea. So since order matters, we know that we want to deal with a permutation where we're selecting 7 things. Of the 7, we're only selecting 3. So then we know the formula for a general permutation. And let me just verify this. I want to make sure I didn't miss something in the denominator. Yes, okay, good. That's our permutation formula. So we need to take our 7 factorial and we divide it by 7 minus 3 factorial. And since there is this parentheses, we do have to do the subtraction before we apply the factorial. And remember, you can't treat factorials as numbers, right? It's hiding multiplication. So we would first simplify this and get 7 factorial over 7 minus 3 is 4 factorial. Okay, but this is not 7/4 because 7 factorial is hiding 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So what you could do is you could either type both of those multiplications into your calculator and correctly divide, or if you'd prefer, we also know that since it's multiplication, there's going to be a lot of cancellation. So you could write out the multiplication, and anything that's above and below multiplication-wise cancels, and it just simplifies to be 7 times 6 times 5. And if we could verify if somebody has their calculator, is that 210? Great, thank you, Jordan. So there are 210 ways that we could select 3 of the books if order matters. Any questions on this so far? Do we see kind of the key signs to use a permutation? Bigger to smaller, order matters. Now, take a moment to read through this one. In words, try to think about what your strategy would be. After y'all do that for a second, I'll write out an important formula. Now in this case, we go from 5 books and we're selecting 2 of them. So do we agree we're going from bigger group to smaller group? So we're starting to think permutation or combination. How do you decide between them? It says order does not matter, which means we should be using combination. Now here's the general formula for combination. Take a moment to set up the problem then. That's a multiplication dot. I think we would get 5 factorial divided by 5 minus 2. You could always mentally calculate that as 3 and immediately write down 3 factorial if you prefer, times 2 factorial. You could either type this into your calculator or write out the multiplication and cancel things, whichever you prefer. And this becomes, what, 20 over 2. So you'll get 10. Did y'all also get 10? Is that good with y'all's calculation? Good. So we've seen how to do permutation and combination. Thank you, Anna. Any questions about these topics or additional problems y'all would like to see before we move on? There's also some problems that just ask us, can you evaluate factorials? Take a moment to think how you would attempt the next 2 and start working on them. The first one is 11 factorial divided by 9 factorial. The second one is parentheses 7 minus 5, close parentheses, then factorial. Correct, Jordan? Well done. Again, if you ever have your answer that you'd like me to check, feel free to send it in the chat. Great job, Anna. Well done. So for the first one, we see it's factorial. So you could write 11 times 10 times 9 all the way down to times 1 in your calculator, divide that by 9 times 8 all the way down to 1. But I think, especially whenever the factorials are very close together, we want to remember there's going to be a lot of cancellation. So if we write out the multiplication, we can cancel a lot before we ever start typing it into our calculator. 9 factorial starts at 9 and multiplies down through all the other integers. And what we notice is all of these are exactly all of these. So we just end up with 11 times 10. Type that into your calculator. You should get 110. Okay, perfect one. Exactly right. Perfect, William. And now for the next one, always remember parentheses take precedent first. So if you've got a parentheses followed by a factorial, you've got to establish what occurs inside the parentheses first before the factorial. So we would say, okay, 7 minus 5 is 2. So this is 2 factorial. Now 2 factorial is 2 times 1, and we should get our final answer of 2. Now, if we wanted to have 7 factorial minus 5 factorial, that would have to be written as this. And that would be a much different value. Does that kind of make sense, the visual difference? Good. So watch out for parentheses. That means do those first. Give everybody a moment to attempt 7. And remember, this is y'all's review, so at any point, if y'all'd like to talk about a topic more or see more examples, just feel free to say that out loud or type it in the chat. Great job, Molly and Jordan. That's correct. Great job, Anasia. Perfect, Juan. Well done. Perfect, Anna. Okay, so I'm seeing correct answers so far from those who are sending it into the chat. The parentheses tell us to divide 12 by 2 first, which would be 6, and then apply factorial. So 6 times 4, 5 times 4 times 3 times 2 times 1. When we type that in our calculator, we should get 720. Great work. Now, we also had this idea when we are arranging letters where there's repeated elements. So a lot of times we had this in the context of words. The idea for that was you would always count the number of letters there are, and that's what's at the top factorial. And then if there were ever any repeat letters, you would count how many repeats there were, and you would divide that by that many factorial. So for instance, if we were looking at the word Alabama, we would say there are 1, 2, 3, 4, 5, 6, 7 letters in all. So I would start with 7 factorial. And then I have to divide by any repeats. So think about what letters repeat here. We've got an A occurring 4 times. So we would then divide by 4 factorial. I don't think there's any other repeat letters. So that would be it. So once we calculate that, 7 factorial divided by 4 factorial. I believe we get 210 again. So there's 210 ways to rearrange the word Alabama.
I have a question.
Yes.
So say like the L may be repeated. How would you write it at the bottom? Like if
Oh,
there was the
yes.
A repeating and the L repeating.
Let's write that out. That's a great question. So I'm going to make this isn't a real word, but it's still okay. Like, let's pretend this is the word that we're figuring out. So do we see now in this case, the number of letters has changed. So we now have 1, 2, 3, 4, 5, 6, 7, 8. So we'd start with 8 factorial letters in all. But then, as it was correctly mentioned, now you're going to have a repetition like the L has been repeated and the A has been repeated. So what you do, the way you deal with that is the repeated stuff always goes at the bottom, and you kind of have each repeated section by itself multiplied together. So we still have the 4 factorial due to the 4 A's, but then we would multiply that in addition by a 2 factorial because of the 2 L's. And then we would calculate
Okay.
it.
I just didn't know if you would multiply or add it.
Yeah, no, great question. You would multiply. And if there was a third letter that was repeated, you would also multiply that there. Okay, and one, does that make sense now why you divide by the 4?
Yes, ma'am.
Okay, perfect. Let me give one more example of this just for practice. I'm trying to think of, it's hard to think of words that have a lot of repetition. Looking at the things around me, I think I have. I would do that, except I don't know how to spell it. Does anybody want to tell us how to spell that one? Okay, if not, I'm looking at one next to me. Let's not calculate this because it would probably be a lot, but let's write out how we would represent it. So transcendentals. Oh, and then I'll write out somebody wrote in Mississippi nicely. We can do that one too. So let's do both of these just for practice.
And drop out.
Now let's work with the transcendentals first. We first want to count how many letters there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And this is one thing I'd recommend. This would probably be a good one to write on your scratch paper, right? So you can kind of carefully count. You don't want to just be looking at the screen. And now let's mark repeat letters. So it looks like A is repeated twice. T is repeated twice. E is repeated.
I think it's 15.
Is it 15? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Perfect. You're exactly right. Thanks for the correction. 15. Okay. So that's corrected. And then I think we also have an N 3 times. And I think the rest do not repeat. Is that a note? We also have the S's repeating. Okay, but I think the rest don't repeat, right? The L is by itself, the R and the C is by itself. Okay, so it'd be 15 factorial. Yeah.
Would we get the 2 A's?
Yes, we would get the 2 A's. So let's just go alphabetically. We've got the 2 A's. And then the next repeated alphabetical, I think, would be the E's, right? And we have 2 E's. Okay, so we've taken care of the A's. We've taken care of the E's. I guess would the N's be next?
Got three N's
3 N's, perfect. 3 N's.
and 2 S.
2S, great work. And then 2 T's, right? Does that match y'all's work? Let's verify there was a lot going on here. So we got the A's, the E's, the N's, the S's, and the T's. Okay. And, we technically could calculate that. Let's just leave it like that. We're kind of setting it up. Let's now go to Mississippi. So we again count how many letters there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If y'all would agree with 11. Factorial. So the total number at top divided by, now let's look at the repeats. I'll give everybody a moment to calculate that. And there are formulas for this. I think we covered this either in 10.1 or 10.2, but just writing down a helpful example might be as helpful as writing the formula, right? Because you can kind of remind yourself, you could write in this is the total number of letters, these are the repeat letters, and then you could extrapolate it to whatever case appears on the final. So for Mississippi, seems like we've got 4 S's, 2 P's. Okay, and then 4 I's. So let's do this in alphabetical order. We'll get the 4 I's first, the 2 P's, and then the 4 S's. Do y'all agree with that? Good. So these problems are quick to recognize because they're the only ones that are asking you how to rearrange letters. Now remember, sometimes in our tests, because we're interacting through the computer exam, you know, if this was just a paper test, you would write in the number as a fraction. Okay. But on the computer, I can't find a way to get the formatting for the boxes to be over each other. So sometimes if your answer isn't a fraction, it will have this box divided by box. And then in the question, it would always say a reminder, this is the way that we format fractions in our exam. So just remember, if it's a fraction answer, you'll have the box divided by box, where the first box is the top number of the fraction, and the second box is the bottom of the fraction. Take a moment to read through and then think about this problem. Remember, probability in words is always the number of ways we can get what we consider a success divided by the total number of options. Now, if we are rolling a 6-sided die, then there are 6 options when we roll it, right? We could get a 1, 2, 3, 4, 5, or 6. So we might really quickly say, okay, the total number is 6. That's the bottom of the fraction. Now let's figure out how many ways, how many of those are we okay with? And one word that we notice is this or. We always deal with or in terms of counting in a very particular way. You always count the number of ways you could do the first thing, plus the number of ways you could do the second thing, minus their intersection. So we would write in like the number of even, plus the number of multiple of 4 outcomes, minus the number of even and multiple of 4. And that's always the formula for or. This one plus this one minus this one. So let's count how many things are even. 2, 4, 6. There's 3 of them that are even. Plus, how many of them are multiples of 4? Well, if multiple is 4, it's like 4 times 1, 4 times 2, 4 times 3. So 4, 8, but 8 is not a die roll. So the only one we can count is 4. So there's only one multiple of 4 in a roll of the die. But then we have to subtract out what they have in common. And do we see what they have in common is this 4, a single option?
What about the 2?
For the even or multiple of 4, Jordan?
Multiple of 4.
Yes, so that would be that's not considered a multiple because you'd have to divide in order to get 2. So when they say
Okay.
multiple, they're like a integer multiple. So like times 1, times 2, times 3.
Okay.
Yeah, good to verify. So the multiples of 4 would be 4, 8, 12, 16, 20, etc. And what do we notice here is that within these 3, didn't we count 4 as part of the first 3? But then what do you notice? You counted 4 again as part of the multiple of 4. That's why you subtract out the intersection to get rid of the overcounting. So we should get 3 divided by 6 is our probability. 3 plus 3, 3 plus 1 minus 1. And what I'd recommend for these problems is, do y'all see that we got a lot of traction when I actually wrote out the options for the die roll, and then I could kind of interact with that on the paper? I think that's helpful. Don't just keep it all in your head. Okay. think about the probability of drawing a face card. Remember, if there are card questions on the exam, do y'all remember that image that was included in our notes and also exams about the cards? So that will be provided again if needed near the problem. But as a reminder, there are 4 different suits in a standard deck of cards. Each of the suits has 3 face cards, king, queen, or jack. So it's asking you, of the total 52 cards in a card deck, what is the probability you get a face card? So think number of ways you could get a face card divided by total. Perfect, Anna, well done. So the total is 52. That doesn't eliminate any of our choices, but we know that there are 3 in each of the 4 suits. So that's 12 in all. Our answer would be A, 12 out of 56. Well done, Jordan. Now here we have a little spinner. What's the probability of getting a red region? Probability is always number of things that you count as a success, in this case landing on red, out of the total number of options. Correct, Jordan? Correct one, well done. Now in this case, let's count. There are 1, 2, 3, 4, 5, 6 regions in all. So I know my total is 6 because as I spin it, I can land on any of those 6 locations. How many of the locations do I want? 1, 2, right? Only 2 of these are red. So there are 2 of the 6 locations that I actually want to land on. So we should get 2/6. Okay. Now, as you read through this, I'd encourage you to think and focus on the word not. Give everybody a minute to attempt that on their own. Half the deck is black, half the deck is red. Correct, Jordan? Would we agree if it says not a red card? Since the card deck is split into red or black cards, right? There's no other option. If it says not a red card, that means that we want to draw a black card. So if we want, we can kind of reverse that in our mind if that helps. And then we think, well, we want a black card because we do not want a red card. How many black cards are there? There are 26 out of 52. And that could be kind of a direct way to get to the problem. Now with not, you could also always say, well, let's take the total amount of things and subtract the things that we don't want. And what's left over is what we do want. So another way you could have done this problem is said, in total, there's 52 out of 52 cards. And I'm going to subtract out the cards that I don't want. Now, what do I not want? Red cards. How many red cards are there? There are 26 over 52. And when we subtract this, we get the 26 out of 52 black cards that are remaining. So that could be a different way to do it. So correct, Anna, as well. So with not, you could mentally switch it, or you could take the total minus the thing that you don't want. Both will work. Okay. Read through this problem and notice this is the kind of reminder about what this fraction box means. Juan, I think that's chapter 10, close to 10.2 or 10.3. I'll verify. Jordan, that's correct. And that picture diagram would be included next to any problems that ask about cards. So if it was in the final, you would have like the picture diagram first and then the card questions. Correct, Anna. Correct, Jordan. I was saying that wrong. It's not chapter 10. It should be chapter 9 for the card question. Or this book is, sorry, I think maybe chapter 11. I was using the previous book's labeling. So it would be in chapter 11. And specifically section 11.2 on page 34 of the class notes. So we know the total is 16. And what do we want? We want it to be fiction. And this gives us the total number of fiction books, right? 3 in each category. So our answer should be 6 out of 16. Now we'll continue here. We are asking about nonfiction and paperback. These should have been 16 when I updated the problem. So from the table, identify those books that are both nonfiction and paperback. Which I'll agree with 2, right? There are 2 books that are both nonfiction and paperback. So of the total 16, 2 of the 1 fit the category that we want to see. Now we also had the phrase given. Remember to see the phrase given as you're just told new information. So what's happened is you were just selecting a book from the 16 and you can't see the book, but your friend has told you, oh, the book that you selected is paperback. So before you were told that information, you didn't know whether you selected a hardback or a paperback, right? So you had 16 options. But do you see if you're told that it's paperback, automatically all the hardcover books, you know that you definitely did not grab them. Okay, so how many books are you really choosing from now that you know that it's paperback? Do we agree? 5? That's the new total. And of those 5 books, how many of them are nonfiction? 2. So the given, you really need to see this as I've been told new information, which resizes my total that I'm looking at. There are formulas for the given, but I think it's easier just to think about it in terms of the problem. Now, the last thing that we learned from these sections is the idea of expected value. Remember, at expected value, you always take the outcome and you multiply it by the probability and then add all of those together. That's how expected value works. So we would type into our calculator 1 times 0.05. Here you want to make sure you don't miss any zeros that could throw off your problem. 2 times 0.10 plus 3 times 0.30 plus 4 . Okay, type all those into the calculator. got 2.7. Does that match others' calculations?